So let's discuss the forces that determine how the wind blows, the speed at which it blows, the direction it blows. We need to understand Newton's laws of motion to help us understand how the wind blows. Newton's first law from physics, you may remember, says that an object at rest will remain at rest, and an object in motion will remain in the same motion as long as no force is exerted on it. So basically, if an object, and it could be a basketball, it could be a baseball, it could be a molecule, right? If it's not moving, if it's at rest, it's not moving any direction or speed, right? If its speed is 0, it's going to stay at rest unless an external force acts on it. And an object that's moving will move in the same speed in the same direction unless a force acts on it. So, for an example of Newton's first law, a baseball in a pitcher's hand, okay, could be Bumgarner's hand, could be Thor's hand, Kershaw's hand, will remain there until a force acts upon the ball, right, when the pitcher throws the ball. Once it's thrown, it would continue to move in that direction forever if it were not for the force of air friction, which slows it down. Typically, the ball moves fastest right when it's released, okay? Maybe when Chapman throws the ball, initially it's 105 miles per hour, and then when it gets to the batter 60 feet 6 inches away, maybe it's 100 miles per hour. So friction slows it down. The force of gravity pulls it toward the ground. Okay, you know how if you throw a ball, a baseball, a football, eventually it starts going down because of gravity. And if the pitcher throws the ball to the catcher's mitt will exert an equal but opposite force on it, which brings it to a halt. So that's why the ball stops moving. Newton's second law says that the force exerted on an object is equal to its mass multiplied by the acceleration produced. F equals ma. Very well-known law in physics. So basically, in order to accelerate, which means to speed up, slow down, or change direction, a force needs to be applied. So acceleration, when you think of it, you might think of, your car accelerating from 0 to 60 real quick. Or, accelerating in the sense turning up 0 to 100 real quick, right, Drake? In science, acceleration can be the changing of speed up, slow down. So positive acceleration we call acceleration usually, but negative acceleration you might call it deceleration, or changing of direction. So actually, if an object's speed remains the same but it moves in a new direction, that's also acceleration. A force needs to be applied, and the force is equal to the mass of the object times the acceleration that is produced when the force acts on it. Now, when air is set into motion, there are many forces acting on it. So question, what are the forces affecting the horizontal movement of air? Well, they include the pressure gradient force. That's a force caused by horizontal differences in pressure. That is the force that initially sets horizontal air into motion, as we've discussed. Coriolis force is a fictitious force, basically, that's caused by the fact that we live on a rotating Earth. Centripetal force is a inward-directed force that applies to objects moving in a circle. And friction is a force that acts close to the ground, where basically the air feels the effect of the ground, which slows it down. There's a reason why as you go higher in the atmosphere, the wind speeds increase, okay? And even if you go, hiking on a mountain, you'll notice the ridge tops where you're exposed to the open air, right, the wind speeds are stronger than close to the ground, the lower elevation where there's more air filling the surface roughness, slowing it down. Now, in order to help understand the pressure gradient force better, you can not just think of air, but you can think of water. You can think of bicycle. Okay. Here's a figure from the book showing two tanks of water connected to each other. And initially, let's say this tank A has more water than tank B. But they're connected. And so there's a net force acting from tank A to tank B because there's higher pressure exerted on the bottom of tank A because of more water, right? Less water in tank B, so lower pressure of the water, right? Force per area at the bottom of tank B. And if these tanks are connected here, then the water will want to move from the region of higher pressure to lower pressure. Okay? And so what will happen is tank A will lose water, its pressure will decrease, tank B will gain water, its pressure will increase, and that will help balance out the difference in pressure. That's why the water moves in this case to restore a balance. Same with air. The reason air wants to move from high to low pressure is to negate, right? Get rid of that difference in pressure caused. So, here's a bicycle, right? Here's the wheel. Here's spokes. Here's the nozzle where you can take air out of the bicycle tire or pump air in. Here's a meter basically showing pressure in pounds per square inch. Recall that average sea level pressure is about 14.6 pounds per square inch. Pressure in bicycle tires is usually much higher. Road tires need a pressure of about 80 to 130 pounds per square inch. Mountain tires need a pressure of 30 to 50 pounds per square inch. Less pressure, they're thinner. And hybrid tires, kind of a balance between the road and mountain tires, typically have desired pressures of 50 to 70 pounds per square inch. If the pressure is too low, right, and this happens over time, the air escapes the tire, that can make the bicycle harder to ride, right? You have to exert more force to pedal. And that can actually increase the risk of flats, right? You don't want to have the pressure too low because it makes flats more likely. And of course, you don't want to have the pressure too much, right? If the pressure is too high, then that runs the risk of the tire popping, exploding, which can damage hearing and run the risk of injury because the sudden outward movement of air. Okay. So by the way, speaking of outward movement of air, if you take the pump off and expose the nozzle to open air, what happens? You hear the effect of air moving out of the bicycle tire to the atmosphere, right? If you take the nozzle off, right, and there's no pump connected, does air from the outside atmosphere go into the tire? No, because what we were saying is the pressure inside the bicycle tire is higher than for the air, and air wants to move from high to low pressure. Okay. Now, differences in horizontal pressure create a net force acting on air, and it's called the pressure gradient force. It can be abbreviated PGF. It's always directed from high to low pressure at right angles, 90-degree angles, perpendicular angles to the isobars. Recall the isobars are lines of constant pressure. The pressure gradient force magnitude, in other words, the strength of the pressure gradient force, is directly related to the pressure gradient. The pressure gradient is the pressure difference per distance. So pressure gradient is basically the change in pressure over a distance. And because we want to understand differences in horizontal air pressure and horizontal winds, we're talking about sea level pressure here. Adjusted sea level pressure, not station pressure. Okay, because we don't want the influence of topography to affect our analysis. The closer the isobars are, okay, the closer the isobars are, the steeper the pressure gradient and the stronger the pressure gradient force and the stronger the winds, greater the wind speed. The greater the spacing in isobars, the more farther apart they are, the less the gradient, the weaker the pressure gradient force, and the lighter the winds. Okay, so where you see on a weather map, a surface map, isobars greatly spaced, right, a region where there's no isobars, then that means calm winds. Where they're really close together, stronger winds. And so for hurricanes, which have a very low pressure at the center, the isobars are extremely closely packed, which is why the winds in a hurricane are so strong, blowing inward toward the center of the storm. Again, the pressure gradient force is responsible for the formation of the horizontal wind. That is the force that gets the horizontal air moving. Without it, the air would not blow. Now, once it starts, horizontal wind starts blowing, then you have the effects of the Coriolis force, friction, centripetal force, but neither of those three forces will initially set the air in motion. Here's a figure from the book showing a region of high pressure here on the left side, shown by the blue H, right? Blue H means a surface high pressure system. Red L means a surface low pressure system. Here are two isobars. Remember, they're on surface maps. They're drawn at 4 millibar intervals, right? Point 1 here is along the 1020 millibar isobar. Point 2 is along the 1016 millibar isobar. And point 1 and point 2 are separated by 100 kilometers, or 62.1 miles. Recall a 10K race is 6.21 miles. So this is about the distance from, San Jose to maybe Sausalito, okay, or San Jose to Martinez along 680, about that. What's the pressure gradient? Recall pressure gradient is pressure difference over distance, 4 millibar difference per divided by, right, 100 kilometers. That's the pressure gradient. The net force directed from higher to lower pressure at right angles to the isobars is called the pressure gradient force. Okay, so it's important to be able to draw the direction of the pressure gradient force on a surface map. And to do that, it's very simple. All you do is draw lines to show the pressure gradient force at right angles to the isobars, and then you remember it's always directed high to low pressure. So the pressure gradient force would not be directed from right to left in this scenario because air wants to move from high to low pressure, not low to high pressure. Now, does the air directly move from high to low pressure in a straight line like this at the in the direction of most rapid pressure decrease with distance? Not quite, because of other forces that can change its direction and slow it down that we'll be discussing. Okay. Here's another figure, this time showing a high pressure area, an anticyclone, right? Notice the 1024 millibar isobar. So inside it, the pressures are even higher. This is significantly higher than average sea level pressure of 1013.25 millibars. And what's shown is the pressure gradient force. Because this is the center of the high, the pressure gradient force acts basically in all directions, right? Because from the center of the high, it can go any direction and be at a right angle to the isobar. But notice the isobar spacing is not the same in all regions around the high. Notice that if this direction is north, right, going from bottom to top, so this would be northwest. Notice going northwest, the pressure decreases faster than going southeast. Okay. Therefore, the pressure gradient force has greater magnitude. It's stronger going from northwest of the high, the center of the high, compared to southeast. That's why this arrow is longer. Okay, even though it still exists in this direction, the pressure gradient force is greater, stronger magnitude going in northwest compared to southeast. Hence, the winds you would expect to be stronger in this vicinity of the high compared to this vicinity of the high. Here's a surface weather map. For 6 a.m. Central Standard Time back on Tuesday, November 10th, 1998. So this is an old surface weather map from about 18 years ago. And it's a nice weather map because it shows a very strong cyclone centered over northwest Iowa. Okay. Dark gray lines are isobars with the units in millibars. There's the interval of the isobars is faux millibars. Deep low with a central pressure of less than 972 millibars here is moving actually toward the east. And you have some information on the diagram. See this blue line with filled in triangles? That's a cold front. Whereas this red line with filled in semicircles is a warm front. And this small purple line here is an occluded front. Okay, we'll talk more about fronts in a couple weeks. Ahead of the cold front, before it's past this area, and basically after the warm front's passed, between the cold front and the warm front, it's called the warm sector of the storm. Typically warm and moist air mass here. And you can help understand that by looking at the direction of the winds. These flags are wind barbs, and the ends of the flags, or the tails of these wind barbs show you where the wind's coming from. Notice it's coming from the south or south-southeast over this part of the country as you go from Indiana, Ohio, southward into Kentucky, Tennessee, and Mississippi, Alabama. That's coming from the warm Gulf, warm moist air. Okay, whereas just behind the cold front, the air is more westerly, colder. Okay, the green line here goes basically from the northern Nebraska, Iowa border to near the Colorado-Nebraska border, okay, here. And the distance is 500 kilometers, but the pressure change over this distance is about 32 millibars. 976 to 1008 millibars. So that was a pressure gradient of 32 millibars in over just 500 kilometers. Very strong pressure gradient, therefore strong winds. The number of lines on the wind barbs shows you wind speed, and where you have 4 of these long lines, that's 40 knot wind. 40 knot wind is about 45 plus miles per hour wind. Okay, so this is some very strong tropical storm force winds. Although this wasn't a tropical storm, this was a fall storm. Notice the pressure gradient over Texas is extremely small, right? There's hardly any isobars over the state, which is why winds are pretty light, 10 miles per hour, right? And for these locations, okay. This bolded dash gray line is a trough. It's basically an area of low pressure, but it's not a cyclone. And since cyclone's an area of low pressure completely circled by at least one isobar, in this case many, whereas a trough is a weaker area of low pressure shown by a bend in the isobars. Notice that the isobars bend toward the south along it. They also do along the cold front, as you can see. Okay, so we understand how the pressure gradient force works and how it influences wind speed. What about these other forces that begin acting on air once it's set into motion? We're going to talk about them, starting with the Coriolis force. Now, it's an apparent force due to the Earth's rotation. It's not a real force by itself, in the sense that it wouldn't exist without the Earth rotating. If the Earth didn't rotate, there would be no Coriolis force. Okay, but it's not a completely fictitious force in the sense that it's a real force since Earth rotates. Okay, now it causes wind to deflect to the right of its intended path in the northern hemisphere, to the left of its intended path in the southern hemisphere. You know, Earth rotates at nearly 1,000 miles per hour near the equator. So basically, if you're on the equator, the Earth is moving at 1,000 miles per hour toward the east. Okay, you're moving very fast. Of course, you don't feel the Earth moving beneath you because you're moving with it. The higher the latitude, the stronger the Coriolis force. It's zero at the equator and reaches a maximum near the poles. So, wind, as it moves from one place to another in the northern hemisphere, will actually not move in a straight line completely, but will not completely move in a straight line, but will get deflected to the right. So if the air wants to move from south to north, it'll get deflected toward the east. And in the southern hemisphere, the wind also gets deflected by the Coriolis force, but in the opposite direction, toward the left of the intended path. And it's important that to understand the direction of deflection, to take your point of view from the direction the object's moving, right? Now, the amount of deflection depends on three factors. The rotation or speed of the rotating Earth, but that's a constant. Earth's rotating at a constant speed. So that's doesn't change over Earth. But the latitude does. The Coriolis force does not exist at the equator, but it's maximum at the poles. It turns out if you're at the North Pole, you're actually not moving any distance. Your distance is not changing, but you're just spinning in a circle. Okay, you're not moving east and having your moving a distance east or a distance west or what have you. You're just spinning in a circle. Okay. The object's speed affects the amount of deflection. The faster the object moves, the greater the Coriolis force acting on it, and the larger the deflection. So for slow-moving objects, the Coriolis that also do not move over a great distance, the deflection will not be much. Okay, misconception is that the Coriolis force is able to cause water to go down the drain a different direction in the northern hemisphere than the southern hemisphere. That's too small a scale. The water doesn't move fast enough, and it's over too small of a spatial scale to get deflected much. Okay. The reason that the deflection of wind or any moving object, could be a baseball, okay, airplane, is the opposite in the southern hemisphere compared to the northern hemisphere is because from a northern hemisphere perspective, the Earth rotates counterclockwise. So if you're on the North Pole looking down, the Earth appears to be rotating counterclockwise. But from a southern hemisphere perspective, if you're on the South Pole looking north, the Earth appears to be rotating clockwise. To help you understand the Coriolis force better, think of a rotating merry-go-round example. Now first, if the merry-go-round is not rotating, it's not moving, a ball thrown from one person to the other would move in a straight line. Okay? But on a rotating platform B, in this case it's rotating counterclockwise from the perspective of above, if you were above here, the ball continues to move in a straight line from the perspective of someone not on the rotating merry-go-round. But from an observer, somebody on the rotating merry-go-round, therefore rotating with it, right, spinning with it, it appears to be deflected to the right of its intended path. So if the person throws it directly across, because the ball is moving on the rotating merry-go-round, it appears to take a veer and the other person would miss it, right? The person here throwing it across has to actually throw it more left of the other person because of this deflection to the right. Airplanes also undergo deflections. Except at the equator, a free-moving object will appear to deviate from its path as the Earth rotates beneath it. The higher the latitude, the greater the deviation. The Coriolis force behaves as a real force, constantly tending to pull the wind. So, here are 3 different airplane flights. Okay, so these airplanes are all at this constant longitude here, but different latitudes. So this one is near the Alaska-Canada border. This one's off the coast of Baja. This one's over the tropics in the central, or maybe central eastern Pacific Ocean. And they all have destinations east along another line of longitude. This plane wants to go across Canada. This one wants to go to just east of Florida. This one wants to go to northern South America. But the 2 flights that are not moving along the equator experience a deviation. Due to the rotating Earth, these flights traveling eastward, assume they travel eastward, right? So their latitude won't change. They should, if the Earth wasn't rotating, they'd travel along these lines of latitude. But because the Earth rotates, okay, from west to east, they get deviated. And look how the direction of deflection is to the right of the intended path. Orient yourself so you're looking forward toward where the plane is going, right? And you see it's to the right of the intended destination, right? So they end up south of where they want to go. Whereas the one on the equator does not actually deviate. By the way, no hurricane or typhoon has ever crossed the equator. And none will, because there's no Coriolis force at the equator. And the Coriolis force, as we'll discuss in more detail, is what helps pull the air inward toward a hurricane or typhoon. The tropical cyclone is a general name for a tropical system that's very strong. Basically, at least hurricane strength, if you're talking about from the North American name. Hurricanes are what these tropical cyclones are called in the central and eastern Pacific Ocean basins, as well as the Atlantic Ocean basins. But in the western Pacific Ocean basin, right, countries like Japan, China, Taiwan, they're called typhoons. Okay, they're also called typhoons over the Middle East. Australia, in the southern or southwestern Pacific Ocean basin, they are called cyclones. Now, as wind speeds increase, the Coriolis force becomes stronger. Remember that the Coriolis force magnitude is dependent on the speed of the object. Okay, so if the wind moves faster, the Coriolis force acting on it will be greater. And the Coriolis force in the northern hemisphere is always directed to the right of the direction of motion. Think about a moving river where the banks are have greater spacing, right? The flow is weaker, slower. But where the river becomes thinner, the speed of the water increases. Similar idea if you think about upper level weather maps and winds in this case. This is an upper level weather map. Now, these 2 lines are isobars showing 940, 944 millibars. Yes, as we've said, contour lines are plotted on upper-level weather maps because upper-level charts are usually for a set pressure level. But for this one, just pretend it's for a constant height showing pressures. Location 1 an object here, could be an air molecule, right, moving with the wind, has a pressure gradient force directed in this direction, probably north, okay, because it's at right angle to the isobars from high to low pressure. See, the pressure's higher here, lower here. And so Coriolis force typically acts at a 180-degree angle to the pressure gradient force, above the level of friction. Okay, above the level of friction, the Coriolis force would have an equal and opposite direction. And so the wind is actually going to blow toward the east. You see, as the wind speed increases, that's caused by a greater pressure gradient force here at point 2, right? The isobars are close together. And so actually what happens is the pressure gradient force increases, which causes the wind to blow faster, right? But then that causes the Coriolis force to increase in magnitude as well, to balance out a larger pressure gradient force. Winds that blow parallel to straight contour lines in the upper levels are called geostrophic winds. They have a balance between the pressure gradient and Coriolis forces. What about for winds around lows and highs, above the level of friction? On the left, you have a low pressure system. Here you see a minimum pressure at the center of this low of below 850 millibars. This could be a 5,000 feet elevation chart, okay, showing pressures at 5,000 feet elevation. And you see you have some curved isobars around this low. Now the pressure gradient force, of course, is directed at right angles to the isobars toward lower pressure. And so what's going to happen is an air parcel here at this point will begin to travel inward toward the low. Now it won't travel directly inward because it's being deflected by Coriolis force, but you can work out the pressure gradient force and Coriolis force magnitudes and directions and find eventually the air parcel will begin moving parallel to the curved isobars. But are the pressure gradient force and Coriolis forces balanced here in this scenario? They're not. Notice that the pressure gradient force arrow is longer than the Coriolis force arrow. So there's a net force directed inward. Why, you ask? Because there has to be, in order for the wind to blow parallel to a curved isobar. Because remember, what is acceleration? Speeding up and or slowing down and or changing of direction, right? So air that's moving here in a circular counterclockwise motion around the low is accelerating, even though the speed isn't changing necessarily, right? The speed isn't changing, it's accelerating because it's changing direction. And what we said was that in order to accelerate, right, F equals ma, there has to be a force acting on it. The force, in this case, is an imbalance between pressure gradient force and Coriolis force. So the pressure gradient force and Coriolis force are not completely balanced. That results, the pressure gradient force is greater and it's directed inward. So therefore there's a net force directed inward toward the low to keep the air moving counterclockwise around the low here. You know what you call that net inward directed force that results from an imbalance between the pressure gradient force and Coriolis force? That is the centripetal force. That's the centripetal force. So the centripetal force is actually the result of an imbalance between the pressure gradient and Coriolis forces. Without those two forces existing, it wouldn't exist. On the other hand, for the high, here, you have a region of high pressure. The pressure gradient force, again, is directed at right angles to the isobars, but in this case, in the other direction, because it's from high to low, so it would be this direction. And air that's outside of this high would eventually begin moving parallel to the curved isobars, but in a clockwise direction. So therefore, the Coriolis force has to be stronger than the pressure gradient force in order for this net inward force to exist that will keep the air moving in a circle, not in a straight line. So, here's a review of some of these key concepts and some important terminology for winds that blow around lows and highs above the level of the friction. So a gradient wind is one that blows at a constant speed but parallel to curved isobars above the level of surface friction. And you may be wondering, how high does the friction extend above the surface? It depends, but generally it's on the order of a few thousand feet. Now, a gradient wind is always accelerating because it's changing direction. Even though the speed isn't changing, the direction is, so it's accelerating. That acceleration caused by changing direction is known as the centripetal acceleration. The centripetal acceleration is directed at 90-degree angles to the wind, inward toward either the cyclone or anticyclone. The net force acting on the wind must be directed inward toward the low or high to keep the air moving in the circular path. Otherwise, it would move in a straight line at the same speed. This inward directed force, that's the imbalance between the pressure gradient force and Coriolis force, is called the centripetal force. Again, the centripetal force is not its own force by itself, but rather caused by an imbalance between these two forces, the pressure gradient and Coriolis forces. And here's the same figure you saw now with centripetal force shown as that net inward directed force. Okay. An upper level weather map shows wind direction indicated by lines that parallel the winds. As you see, you've seen this before. Now we have height contours, higher toward the south where it's warmer, lower values toward the north where it's colder, and the wind barbs are blowing, winds are blowing parallel to the contour lines. See how the wind barbs are oriented in the same direction as the contour lines. And that's due to no friction, only pressure gradient force and Coriolis force. Where the lines are straight, there's a balance between the pressure gradient and Coriolis forces, and a gradient wind flows. Excuse me, a geostrophic wind flows. But around curved contour lines, the pressure gradient force and Coriolis forces are the only real forces in acting on the air. But in order to keep the air moving, changing direction, around this high here, this ridge, there has to be a net inward directed force, and that's the centripetal force. So the wind blowing here on this curved high is called a gradient wind, whereas the wind blowing when the contour lines are straight is known as a geostrophic wind. And here's a trough here over the west coast, associated with colder air, as you see by the lower isotherm values in degrees Celsius. By the way, where winds are oriented west to east, in the upper levels, we say there's zonal flow. Zonal flow means winds blowing from west to east at along a constant line of latitude, not changing latitude. Now, what's really interesting is that above the level of friction, if you know which way the air is moving, there will always be lower pressure to the left and higher pressure to the right. In the northern hemisphere, above the level of friction, there's always lower pressure to the left, higher pressure to the right of the direction of motion. Now, what about at the surface? Because that's where we are, right? We want to start understanding what's different about the forces acting on wind at the surface compared to above the level of friction. Now, winds on a surface weather map do not blow parallel to the isobars, unlike for an upper level weather map, which shows winds above the level of friction, but they cross from higher to lower pressure at an angle. The angle varies, but it's typically about 30 degrees, okay, so a slight angle, an acute angle, right? The angle is greater over rougher surfaces and less over the ocean. So actually the ocean is very smooth, and so there's not nearly as much friction over the ocean compared to land. So over the ocean, the winds are closer to geostrophic or gradient. Frictional drag of the ground slows the wind down. That rhymes. Wind speeds increase with height above the ground due to a lack of friction. So here's an upper level weather map. You see straight contour lines, lower pressure toward the north, higher pressure toward the south. There's a balance between pressure gradient force and Coriolis force, and the winds blow parallel to the contours. Around a low, a trough, the winds still blow parallel to the curved lines, but there would have to be a net inward directed force here. A gradient wind blows. A gradient wind blows around this ridge of high pressure. Notice, no matter if the contour lines on an upper level weather map are straight or curved, the winds still blow parallel to the contour lines. And the way to know which direction they blow is to remember that lower pressure needs to be on the left of the direction of motion, higher pressure on the right. Now on the ground, the winds do not blow parallel to the isobars, because what happens is, if initially there's a balance between the pressure gradient and Coriolis forces, friction comes into play and slows the wind down. And you can work out the diagrams to show you that eventually here, if you don't have friction, and then you start to incorporate friction as the wind begins to blow, it slows the wind down, and a slowing of the wind does what to the Coriolis force magnitude? Slower the wind, weaker the Coriolis force. Now the Coriolis force would be less than the pressure gradient force, but in the same opposite direction, but less magnitude, so it would be shorter. And then that would cause the wind to begin to curve, because yes, there's two forces acting in opposite directions, but the pressure gradient force has a greater magnitude, so the wind would begin to curve toward the left, in this case, okay, toward the pressure gradient force direction. And then that will change the direction of the Coriolis force, because of course the Coriolis force has to act always at a right angle to the direction of motion. Friction always acts at in a direction opposite the direction of motion, because the sole effect of friction alone is to slow the wind down. But once that happens, that changes the direction of the wind, because the Coriolis force does not balance the pressure gradient force. And you see in the northern hemisphere, winds blow counterclockwise and inward around lows, clockwise and outward around highs. Aloft, though, winds blow parallel to contour lines in a wavy west to east pattern. Now, you can estimate wind direction and pressure patterns in the upper levels or aloft by watching clouds. Here you are on the bicycle. You're going on a ride toward the north. And let's say you see a nice cumulus, maybe a cumulus congestus cloud above you, moving from southwest to northeast. Well, if you see it moving from southwest to northeast, you know it's being carried by the wind direction at that level. Therefore, you know the wind direction is southwest to northeast. And then remember what we said, that lower pressure is on the left of the direction of wind aloft, higher pressure on the right. So you know there's lower pressure toward the northwest, higher pressure toward the southeast. And then you can kind of work outward and look at a more zoom outward, and because we know that the winds aloft tend to blow in a wavy pattern, you know there would be a ridge toward the southeast and a trough toward the northwest. Cold air associated with the trough in the upper levels, warmer air associated with the ridge, the upper level ridge. Now, in the southern hemisphere, surface winds also feel the effect of friction, but in the southern hemisphere, the Coriolis force acts in the opposite direction. due to the fact that the Coriolis force appears to rotate in the opposite direction when viewed from the South Pole compared to viewing from the view from the North Pole when you look at the Northern Hemisphere. So here's a December day in South America, right? Here's Chile, Santiago, here's Buenos Aires, Argentina. And you see lows, here's a couple lows. Look how the winds are blowing. They're crossing the isobars, blowing toward the center of the low, but they're blowing clockwise and inward. And around the high, they're blowing outward, but counterclockwise and outward. Now, in order to really understand the meteorology of the atmosphere, you need to think in 3 dimensions, okay? Because we're going to talk about this. It's not just how air blows at the surface, but how it blows aloft that influences not only the direction that highs and lows at the surface move, but whether they strengthen or weaken. And at the surface, an area of low pressure is associated with convergence in the northern hemisphere, counterclockwise and inward air. But then what happens is air rises above the low. Air blows counterclockwise and inward toward the low, right? Now air can't just pile up, so it has to, and it can't go into the ground, so it rises. And that can produce clouds. Eventually, at higher altitudes, the air begins to spread out, it can reach the tropopause, and air diverges. For a surface high, the winds blow, in the northern hemisphere, the winds blow clockwise and outward, and so, as you can understand, the air has to sink above the high, because that air that's blowing clockwise and outward has to originate from somewhere, right? There has to be air coming down to replace it, or you can think of it that way. So in order for that to happen, there has to be air coming together in the upper levels. If upper level divergence exceeds a surface convergence for a low pressure system, the low will strengthen. Whereas if upper level divergence is less than surface convergence, the low will weaken. On the other hand, for a high pressure system at the surface, if upper level convergence exceeds surface divergence, the high will strengthen because you're adding in more air than letting it out for the column, right? And if upper level convergence is less than surface divergence, you're removing air from the column above the high, and so it will weaken. Okay. By the way, the rate at which air rises above a low or descends above a high is small compared to the horizontal winds that spiral about these systems. Generally, the vertical motions are usually only about several centimeters per second, or perhaps a mile per day, right? Compared to miles to tens of miles per hour for horizontal winds. For the low, just to review, if there's greater divergence than surface at the upper levels than convergence at the surface, think about it. You're having a net removal of air from the column above the low that takes away air. That's why the pressure drops at the surface and the storm becomes stronger. Now, the reason that upward and downward motions of air above highs and lows, or lows and highs, the way I said it, for upward and downward motion, the reason that those motions are small is because usually the atmosphere is in or fairly close to a state of hydrostatic balance, which means the upward directed pressure gradient force is equal in magnitude, the opposite direction of the force of gravity, which of course you know acts in a downward direction toward the center of Earth. When these two forces are in exact balance, the air is said to be in hydrostatic equilibrium or hydrostatic balance. When the air is in hydrostatic balance, because these two opposite directed forces are equal to each other, they cancel each other out. So there's no net vertical force, F equals ma, so there's no net vertical acceleration. But sometimes in very strong thunderstorms, you can have fast-moving updrafts on the order of 30, 50, 60 miles per hour, where there might not be hydrostatic balance. Okay, air can accelerate upward. Now, we are understanding what sets air into motion, and once it goes into motion, the forces that act on it, and we understand how to determine wind speed and direction from looking at upper level maps, looking at cloud movement, right? Now, when we're talking about winds, how do we measure winds? How do we determine winds? What's meant by a south wind? Okay, let's talk about winds now in more detail. Wind is characterized by its direction, speed, and gustiness. There's generally two components of wind, right? To completely describe it, you need to describe the direction it's coming from, but you also need to describe the direction at which it's moving, right? Direction's very important, okay? Sure, wind speed is important. You know, it determines whether a few leaves blow, move a few inches on the ground, or whether a roof is in jeopardy of being taken off. But the direction really matters too, right? Whether you're flying into the wind or out of the wind in an airplane. There's a reason why most of the time the airplanes at San Jose Airport that are taking off fly toward the north, okay? Generally because the prevailing wind direction in San Jose tends to be from the northwest, and they want to fly into the wind to take off to generate lift. But ahead of cold fronts, you'll see ahead of storms we get in the wintertime and the late fall and early spring as well in the Bay Area, the airplanes will begin taking off from San Jose Airport toward the south, because the winds are coming from the south and they want to take off into the direction of the wind. Again, as we mentioned before, if you fly from the west coast to the east coast, you save about an hour comparing to flying from the east coast to the west coast, same cities, because of the jet stream. High speed winds aloft generally moves west to east. Now, the sustained wind speed is a 1 minute average wind speed. Gust speeds are typically higher than the 1 minute average wind speeds. Generally, gusts add on 1/3 to 1/2 of the sustained wind speed. So, for example, if there's a sustained wind blowing at, say, south 30 miles per hour, there would be gusts of 1/3 of 30 is 10 to 1/2 of 30 is 15. There would be gusts of 40 to 45 miles per hour. Okay? The gusts, are those sudden, quick bursts of stronger winds that last on the order of a few to several seconds, right? Remember that wind speed is described by the direction at which the wind is coming from, not going to. An onshore wind blows from water to land. Okay? It's also known as a sea breeze. When you're dealing with the water being ocean. If you're near the Great Lakes, you might call an onshore wind a lake breeze. An offshore wind blows from land to water is sometimes known as a land breeze. Okay. When the Bay Area gets very strong onshore winds in the summertime, that can allow the marine layer, the fog, to protrude very far inland, keep it cool. When the Bay Area gets strong offshore winds in the summertime, that can allow places like San Francisco and Half Moon Bay to warm into the 90s. Okay. Because the air is coming from warmer inland areas. A prevailing wind is the wind direction most often observed during a given time period at a given location. Generally, for San Jose, it's from the northwest. Wind direction can be expressed in degrees about a circle or as compass points. So, typically, when you hear wind direction described, you're hearing the cardinal direction, right? The four major cardinal directions are north, east, south, and west. Then, of course, you can use multiple right directions, if you will. You can combine these cardinal directions to be more precise. Okay, a northwest wind blows halfway between from the west and from the north, right? A north-northwest wind would be more northerly, right, than westerly. But you can also describe the wind direction in angles, in degrees. North is given a degree value of 0 or 360 degrees. East is at a 90-degree angle from north, so it's 90 degrees. A wind blowing from the south has an angle value of 180 degrees, or 180 meteorological degrees, and a west wind has a meteorological value of 270 degrees. Okay, so northwest, as you see, it's halfway between west and north. The difference between west and north is 90 degrees. Half of that is 45 degrees, so a northwest wind would have a meteorological angle of 270 plus 45 equals 315 degrees. Strong prevailing winds can have interesting effects on vegetation. Here are some trees that are standing unprotected from the strong prevailing winds and are sculpted into flag trees. Why are they called that? Because notice you tend to only see the branches on the one side, okay, because they've been made into this shape because of a strong prevailing winds coming from left going toward right. What meteorological instrument is used to measure wind speed? Which one to measure wind direction? Well, a wind vane measures wind direction, and an anemometer measures wind speed. Okay, so very old yet still reliable weather instrument for determining wind direction is the wind vane. Most wind vanes consist of a long arrow with a tail, which is allowed to move freely about a vertical post. The arrow always points into the wind, and hence always gives the wind direction. Wind vanes can be made from almost any material. At airports, a cone-shaped bag opened at both ends so that it extends horizontally as the wind blows through it, sits near the runway. And this form of a wind vane, known as a wind sock, enables pilots to tell the surface wind direction when landing, so they can adjust their final descent accordingly, right? Now, the instrument that measures wind speed is the anemometer. Most anemometers consist of 3, sometimes more, hemispherical cups mounted on a vertical shaft. The difference in wind pressure from one side of a cup to the other side causes the cup to spin about the shaft. The rate at which the cups rotate is directly proportional to the speed of the wind, right? The faster the wind, the greater the faster the cups rotate. And the spinning of the cups is usually translated into wind speed through a system of gears, which may be read from a dial or transmitted to a recorder. Now, there are also meteorological instruments that can measure both wind direction and speed. The arrow vane, also sometimes known as the sky vane, measures both wind direction and wind speed. It consists of a bladed propeller here that rotates at a rate proportional to the wind speed, like for the cup anemometer. Its streamlined shape and a vertical fin helps keep the blades facing into the wind. And when it's attached to a recorder, when it transmits information to a receiver, a continuous record of both wind speed and direction is obtained. It's basically a combination of an anemometer and a wind vane, all in one, right? And by the way, wind movement has applications for electricity generation. A wind farm near Tehachapi Pass, California, generates electricity that is sold to Southern California. Okay. By the way, the Altamont Wind Pass, right, east of Livermore, along Altamont Pass, right, north of Interstate 580, still has almost 5,000 operating wind turbines. Still one of the largest collections of wind turbines in an area in the world. And as of 2015, about 6% of California's electricity was generated from wind.